Good morning, everyone. At least here it's morning, so I'm not sure what it is when you watch this recording, but here it's still before 12. So this is the first recording for week 2, and in this week and also in this recording, we're going to talk about refinements of Bayesian Nash equilibrium, And we're going to do that in the context of extensive form games. It would be nice if we can move. Yes. And before we go into the definitions and all the notions that are related to this, maybe a very brief motivation, what it is about. We've seen last week what the Bayesian Nash equilibrium is, and perhaps you already know what the Nash equilibrium in general is from previous courses, at least I hope so. But you may also know that not all Nash equilibria or Bayesian Nash equilibria are equally convincing. So Nash equilibrium in that sense is, you could say, a positive notion. It says that if you have a certain interactive situation between different agents, then if you reach a status quo within that setting, you'll probably end up in a Nash equilibrium, because if it's not a Nash equilibrium, then somebody has a reason or an incentive, as we say, to deviate from the current actions that he or she is taking. So you will end up in a Nash equilibrium if you end up anywhere. However, Nash equilibrium is not a notion that then dictates what should happen, because there can be many Nash equilibria in a given game or a given setting, and they can qualitatively, you could say, differ quite a lot. And refinement theory is, you could say, an attempt to differentiate between different types of Nash equilibria. So here it says, for example, Nash equilibria may well use what are called non-credible threats or weakly dominated strategies, and we would like to focus on Nash equilibria that do not have such, you could say, questionable features. Okay, so here's a very simple example. It's a 2x2 game, 2 players. Player 1 has to choose between up and down, and player 2 has to choose between left and right. And as you can see, all choices result in a payoff of 0 for both, except U and L, the combination, which gives both players 1-1. So you might consider playing U for player 1 and playing L for player 2 the most likely outcome in this game. Nevertheless, DR is also a Nash equilibrium. Why is that? Well, so what do you have to test if you want to test for a Nash equilibrium? You focus on one of the players, for example, player 1, and you fix the strategy that the other player is employing. So maybe I can write that here. So we're going to focus on D and R. So this is what player 1 is choosing, and this is what player 2 is choosing. So if you want to check whether playing D is the best response for player 1, then you fix the strategy of player 2. So he is currently playing R. And then given that, what can player 1 do? Well, he can choose up and then he gets 0, or he can choose down and then he gets 0 as well. And so this is 0 and this is 0. So playing down is one of the best responses. There's 2 best responses, and so both up and down is one of them. And the same holds for player 2. If player 1 is choosing D. Then we are in the lower row of this matrix. And then player 2 can choose between playing left and getting 0, or playing right and getting 0 as well. So also he has two best responses, one of them being R. So indeed, this pair of strategies D and R has a property that they are what are called mutual best responses. In other words, this is a Nash equilibrium. But of course, it's not a Nash equilibrium that you would expect to be materialized in this game. You would expect the players to choose U and L. And Nash equilibrium does not make that distinction. We do this. Maybe like this. So this is an example in a bimatrix game. I also prepared an example in an extensive form game. And that's over here. So this is what's called an extensive form game or a tree game. And what you see here is this is a tree game with two players, also player 1 and player 2. And player 1 has two choices between left and right. So that's indicated over here, right? Left and right. Left and right. And player 2 observes that choice. And if player 1 chose left, then player 2 can choose between A and B. And if player 1 chose right, then player 2 can choose between C and D. And this game has several Nash equilibria. The one that you might anticipate to happen is the one where player 2 chooses B over here, and he chooses C over here, and then player 1 will choose L. So this is the Nash equilibrium that most people come up with, but I will try to convince you that there are other Nash equilibria than this one. So this is a Nash equilibrium, that's not the problem, but there are more. And in order to figure that out, maybe the thing to do is the following. What I'm going to do for you is to draw what is called the associated normal form or strategic form. So this is a game in extensive form. And I'm going to draw the associated strategic form. Not draw, compute. It's a bad word. How does that work? Well, if you want to compute a strategic form for this game, you actually have to figure out what are the strategies of a player in this game. And we already talked about that in the incomplete information game. So this is a game with complete information in the sense that at every time moment in the game, the players know what happened before, so they know exactly where they are in this tree. But you can still compute the strategy. So the left and right and A and B and C and D are actions, but a strategy is like before, a kind of ex-ante plan of action that states for every decision node of a player, what that player would do if he would be in that specific situation. Now, for player 1, this is easy. Player 1 has only one place where he has to make a decision, namely at the start of the game. So his actions are actually his strategies. He only has left and right. So let me write that down. However, for player 2, the situation is a bit more complicated because he has two places where he has to make a decision, namely in the left node after player 1 chose left and in the right node after player 1 chose right. And in each of these cases, he has two actions that he can choose from, A and B on the left-hand side and C and D on the right-hand side. And what is now a strategy? A strategy is a specification of the action that he chooses on the left-hand side, combined with an action that he chooses if we end up on the right-hand side of this diagram. And in both cases, he has two choices possible. So that means that the total number of strategies is 2 times 2. He can choose A on the left-hand side and C on the right-hand side, A on the left-hand side or D on the right-hand side, and 2 more where he chooses B. So what are now his strategies? Like I said, A and C. And so I choose A on the left-hand side and C on the right-hand side. Same way we have A and D, B and C, and B and D. And yeah, now you can actually compute the payoffs. So if player 1 chooses L and player 2 chooses AC, then of course only the A is relevant here. So this could be 0 and 0. And the same here, right? So only A is relevant. And here only B is relevant. And for right, so only C is relevant here, 2 and 6. And here 0, 0. Again, 2 and 6, and 0 and 0. So this is the strategic form of this extensive form game. It looks a bit redundant to also indicate what you would do in situations that do not occur. But if you want to check for Nash equilibrium, that's actually information that you need. If you want to know whether player 1 choosing L and player 2 choosing B is a Nash equilibrium, then you would also, at least in general, have to know what happens if you would have chose something else. So if player 1 chose R instead. So that may matter, and we'll see that that matters. But let's first compute the Nash equilibria over here. So how do we do that? Well, there's a very simple way to do that. What you're going to do is first look at all the strategies of this player over here, let's say AC. Then what are the best responses for player 1? Well, if he chooses L, he gets 0. And if he chooses R, he gets 2. So in this case, the best thing that he can do is to choose R. If player 2 chooses AD, then both choices give player 1 a payoff of 0. So in this case, he is indifferent. Both strategies are best responses. And for BC, he has a choice between getting 6 or getting 2. Then of course, he will go for 6. And the same here, choice between 6 and 0. So left for 6 is the best response. And now you can do the same for player 2. So you fix the strategy of your opponent, you are player 2. So, and your opponent, suppose that he plays L. Then you have a choice between choosing the first column, payoff 0, second column, payoff 0, third column, payoff 2, and the fourth column, payoff 2. So you got 2 best responses, namely to choose either the third or the fourth column. And the same for the second row. So the payoffs that are possible are 6, 0, 6, and 0. So you choose one of the 2 6s. And in total, we find 3 Nash equilibria. So Nash equilibrium now is a cell in the matrix where both players have a star and their mutual best responses. So that's player 1 choosing R and player 2 choosing AC. Player 1 choosing L and player 2 choosing B, C. And here L and B D. Yeah, so, and which one shall I take? Maybe this one here is an interesting one. So what happens is that player 1 chooses R, right? And player 2 chooses A in the left decision node and C in the right hand side decision node. So why is this in Nash equilibrium? Well, maybe first checking that. Given that player 1 chooses R, what are the best responses for player 2? Well, he has a choice between getting 6 and 0. So anything that gives him 6 is the best response. So that is either AC or BC. And you can see that over here, right? So if player 1 chooses R, then player 2 has 2 best responses, AC and BC. So AC is one of the 2 best responses. The other way around, if player 2, given that player 2 is choosing AC for whatever reason, right? So you may question whether it's a clever thing to do or a likely thing to do, but the only thing for Nash equilibrium that is important is that if player 2 chooses that, is then what player 1 is choosing a best response. That's all we need to check. And is that the case? Well, if player 1 chooses left, then he ends up here and getting 0. And if he chooses right, we end up over here and player 1 gets 2. So indeed, the only thing that you can do is to choose R. You may think, is this a likely Nash equilibrium? I don't know. So of course, what does happen is that player 2 is making a questionable choice over here in this node because he chooses A, and that is also bad for himself, right? So that is what is peculiar about this Nash equilibrium. Is that then a stupid thing to do? Well, I don't know. So you see, if you would choose one of the other 2 Nash equilibria, then we end up over here, and then player 2 has a payoff of 2. And now in this Nash equilibrium, and so here the payoffs are 6 and 2, and also here the payoffs are 6 and 2, and here it's 2 and 6. So is it a stupid thing to do for player 2? Well, not from a pragmatic point of view, because he gets 6 rather than 2. Is it believable? Huh? So this hinges on the fact that player 2 can threaten player 1. He can say, if you choose L, then I will choose A, and that's bad for both of us. The question is, does player 1 believe that bluff? If it is bluff, right? So if player 2 is really going to do that, then it's not bluff. But the question is, does player 1 believe that player 2 will actually go through with that plan if he chooses L? Okay, so that is a bit more motivation than I initially thought of giving, but this is exactly the issue. So this is about the backwards induction outcome. So the refinement that everybody thinks that should happen is actually where indeed player 2 chooses B over here and C over here, and then player 1 chooses L. So that is, I think, the equilibrium that most people will come up with. That's this one over here, if you give them this gain. Good. So that's what we're going to actually formalize a bit more. And not just in this one particular example. So here we are. Like I said, yeah, that's what we see now. Huh? So we try to rule out these kind of peculiar equilibria that are not very convincing. And the first attempt to do that is called subgame perfect equilibrium. What is subgame perfect equilibrium? Well, the first thing that you have to know is what is a subgame. And a subgame is, you could say, a part of the tree. Huh? So we're now talking about the extensive form games, so that are modeled by a tree, like I drew just now. And a subgame of such a game is a part of the tree, so a subtree of the game tree, such that if we have what are called information sets that are non-singleton, then such an information set is either completely contained in the subtree or completely contained in the part outside the subtree. Here's an example. Here is an extensive form game with one single non-singleton information set, namely this one over here. It's usually indicated by these dotted lines. So this is a non-singleton information set. It's called non-singleton because it has two decision nodes for player 2. And so there's a 2 here that says that this is an information set where player 2 has to make a decision. And what does it indicate? Well, it indicates the following. So here player 1. So this is a game where we start over here. So first player 1 chooses 1 or 2. And then it's again his turn in both cases. So if he chooses 1, then he has to choose between A, B, and C. And if he chooses 2, he has to choose between left and right. And in this case, he has to choose between A and B and C. And what does this information set now signify? It says that player 2 can see whether player 1 chose A or not. So he does get the information about, did player 1 choose A or did he not? But he cannot observe, if player 1 did not choose A, whether he chose B or C. So that is what this information set indicates. It simply says the only information player 2 gets is, did player 1 choose A or not? Okay, so so what are now subgames? Subgames are parts of the game tree with the property that if you have such a non-singleton information set, then it's either completely contained in the subgame or completely outside the subgame. So the entire game is a subgame, but also this here, for example. So you can see that this part of the game does not have this subgame. And it's not overlapping with that information set. That's what I want to say. This is information set, and it's completely outside that part of the tree. In the same way, this is a subgame because it includes the information set. What else are subgames? So this is a subgame. So it's a one-player game, you could say. And in the same way, this is a subgame. It's a one-player game. However, this over here is not a subgame. It is, of course, a subtree. But it does have the property that one of the nodes of this information set is inside this tree and the other one is outside. So that violates the second condition for being a subgame. So in total, we have 1, 2, 3, 4, 5 subgames here. So that's how you count subgames. As you can see, by the way, this subgame here is the game that we talked about earlier. So let's see that again. Now, what is a subgame perfect equilibrium? A subgame perfect equilibrium is a strategy profile for the extensive form game with the property that in every subgame, the Nash equilibrium, the strategies that form the Nash equilibrium are a Nash equilibrium in that subgame. So you have a Nash equilibrium for the entire game. And if you want to check whether it's a subgame perfect equilibrium, what do you need to do? You need to look at each and every subgame and check whether the strategies that pertain to that particular part of the game tree constitute the Nash equilibrium of that subgame. For example, this here is a Nash equilibrium. So the red arrows indicate the strategy for player 1 and the blue arrows for player 2. So maybe this also requires, or at least it would help with a bit more information. So maybe a good thing to realize first is what is now a strategy for each player. For player 1, well, he has a decision node over here. He has a decision node over here. And you got a decision node over here. And in strategies, has to specify in each of these 3 nodes what he will choose. So for example, this here says in the first node, I choose A. In this one on the left-hand side, I choose, I. In the second one, I choose A. And in this one over here, I choose L. So in total, he will have 2 times 3 times 2, which is 12 strategies. And this is one of the 12. In the same way for player 2, well, player 2 has actually 3 places where he has to make a choice. Of course, there is this one over here, right, where he has 2 choices. And also over here, he's got 2 choices. But this here is a bit is interesting because this is one information set, and that means that since he does not know in which node he is, he can also not condition his choice on being in the left or the right node of this info set. So in this info set, he only has 2 choices, left or right. He cannot say, well, if I'm here, I choose left, while when I'm here, I choose right, because he can't see the difference between the 2. So he either chooses left for both nodes or right for both nodes. That's the effect of an information set. So then in total, how many strategies? Well, he's got 2 choices in the non-singleton information set and also 2 choices in the singleton information sets that he has. So that's a total of 8. And again, this is one of them. Good. And the claim is that this is a Nash equilibrium. Why is that? Maybe it's a good thing just to check it. Let's check best responses for player 2. So given the strategy of player 1, right? So you fix the strategy of your opponent. What are the payoffs if you choose certain strategies? Well, what happens in the game is that player 1 first chooses I and then he chooses A. So that means that we end up over here. Which means that effectively, none of the choices of player 2 has any effect on the outcome. In other words, every strategy gives player 2 a payoff of 8. Right, so he gets 8 over here. And that means that everything is best response. He's got 8 strategies, and each of these is the best response. Among those, LAD. Good. Conversely, for player 1, given the strategy of player 2, LAD, that's indicated by the blue lines. So what can player 1 do? Well, if he chooses to go, what are his possibilities? So he can go here, right? So he can, of course, go here for a payoff of 1. And so he can get 1. Or he can go over here, and then player 2 goes over here and he gets 0. He can go over here, and then we go over there, and then he gets 0. Player 2 can choose 2 and then L, and then we go here and he gets 0. And yeah, so the other option to go here and then there, and then we go here and we again get 0. So you see what he's currently doing gives him a payoff of 1, and everything else gives him a payoff of 0. So he has to choose I and A. What he's doing over here is irrelevant. So he's got 2 best responses. Namely I, A, L and I, A, R. And this is one of the best responses. So indeed, this is a Nash equilibrium. It's not an SPE, so not a subgame perfect equilibrium. Why not? Well, because in this subgame over here that we looked at before, LAD is not a Nash equilibrium, right? So we already computed the Nash equilibrium for this subgame. And we had, what did we have? We had R and, what was it? AC, right? That's the one that we analyzed. And then we have L and BC. And L and BD. Those were the 3 Nash equilibria for this game that we computed earlier. And LAD is not one of them. You can of course see that it's not a Nash equilibrium, but because if player 1 chooses L, then player 2 should choose B rather than A. And so in particular, AD is not the best response against L. It's good to simply write that down. AD is not the best response for player 2 against player 1 choosing L. So that's why it's not an SPE. Okay. So far so good, I hope. What we have here is an SPE. Because you see what you can do now, maybe that's a good thing to do, is to figure out how an SPE should look like. How do you do that? Well, there is something that's called backwards induction. So it's always a very useful technique to figure out subgame perfect equilibria. So what you do is you start at the the lowest level in the game, so the last decision nodes before the game ends. So for example, over here, this is a subgame, and it's effectively a one-player game. And what is now the Nash equilibrium in this game? Well, there's only player 2 playing this game. If he chooses A, he gets 0, and if he chooses B, he gets 2. So he should choose B over here. So any subgame equilibrium, any subgame perfect equilibrium in this game will have player 2 choosing B in this decision node. In the same way, any SPE will have player 2 choosing C in this decision node. And you can actually go on reasoning backwards. Given this, you can decide then what should happen over here. Because if you have a subgame perfect equilibrium, then you already know that player 2 chooses B over here and C over there. And then what can player 1 do over here? Well, if he chooses left, we go over here and he gets 6. And if he chooses right, we go over here and he gets 2. So he should choose L. And that means that any subgame perfect equilibrium should do exactly this in this part of the game tree. So any SPE in this game is of the form well, for player 1, we don't know what he's going to do over here, whether he chooses 1 or 2. So this we don't know yet. Also here, we don't know whether he's going to choose A, B, or C. But he will choose L. And for player 2, we don't know what he's going to do in this part here, but he will choose B and C. By the way, so we cannot do the same. So I forgot to say that so far. We cannot do the same over here, right? Because we don't know what will happen in this game. So this is the other subgame that we would have to analyze. But because of this non-singleton information set, it's not so clear what will happen in this part of the game tree. We cannot use this backward induction principle to completely analyze that part of the game. So that's why it's still it still depends what will happen there. At least on the right-hand side of the diagram, we know exactly what will happen. Okay, so so let me check. This over here is an example of a subgame perfect equilibrium. We already decided that L and B and C are mandatory, but you can also check that 2A and L, right? So maybe give it a different color. 2A and L that is what is happening over here. So player 2 choosing A here, and player 1 choosing A here, and player 2 choosing L. That is a Nash equilibrium in this subgame. Why is that? Well, player 2 is doing something out of the ordinary. He is threatening player 1 to go here to the zeros if he chooses B or C. So player 1 does not do that in this game. He chooses A for the 1 rather than the zeros down here. And so that's A is best response against L. And so this A here is the best response against that L for player 2. And conversely, if player 1 chooses A, yeah, then anything is the best response of player 2. So in particular, choosing L in this orange subgame, right? So that's a Nash equilibrium, and then you can check that then letting player 1 choosing 2 over here is then also a Nash equilibrium for the entire game. And so if he goes to this part of the game tree, then we end up with 1 for player 1, and over here he gets 6, which is a lot better than 1. So he chooses 2. Good, so this is an SPE. Is it now a very credible equilibrium? It is an SPE. Is it credible? Well, in this part of the game tree, I guess it's credible. But over here, you may still have your doubts. Because here, player 2 is still, at least in this information set, doing something rather peculiar. And there is a further refinement, so a refinement of this refinement, you could say, that is going to rule that out, and that is perfect Bayesian equilibrium. But I think given the time, I will stop here and talk about perfect Bayesian equilibrium in the next few recordings. So see you in the next recording.